Okie dokie. We're going to look at a particle physics reaction here, and that is we're going to take a pi minus meson and strike it against, or actually have them both start off with a rest at rest, or very close to rest. Let's just say their velocities will be very much smaller than the speed of light. So we're going to essentially assume that both these particles are at rest, and they're going to create a neutron and a pi naught, or a neutral pion. This is a pi minus, and this is a proton right here. These two will come together, fuse, if you will, and then fission into a neutron and a neutral pion, or pi naught, as it is known. So here's our question right here. Let's take a really quick look at it. If the pi minus meson and the proton are at rest, what are the kinetic energies of the neutron and the pi naught here? So here's our reaction right here. And again, we'll start these guys off. Of course, they won't have velocities equal to 0 because they'll come together, because this is positively charged and that's negative charge. But we're going to assume their velocities are very much smaller than the speed of light. So here's our reaction. Again, as we did in other particle physics things, we're just going to simplify the symbolism here. So the pi meson will be A, represented by A. The proton will be B. The neutron will be C, and the pi naught will be D, represented by D. Here are our formulas, which again I will not derive in this lecture, just because I want to make these lectures less than 10 minutes long. But one day hopefully I'll get the derivation if people want it, or they can look it up, a derivation. Although I've kind of customized my derivation a little bit easier. That's my job, is to make life a lot easier for particle physicists. And but this formula is a standard formula in particle physics. So we have the total energy of the C particle, which is the neutron, is the rest energy of the A particle plus the rest energy of the B particle, which of course will be the pi minus and the proton, divided by 2, plus the rest energy of the C particle squared minus the rest energy of the D particle squared, which of course will be the neutron for the C and the pi naught for the D, over 2 times rest energy of A plus the rest energy of B, which will be these two, or the pi minus and the proton will go here, their rest energies. So let's calculate this real quickly here. Here I substituted all the values in. Here I have the values for each of them. You can get those out of books or Google or whatever. The rest energy of the pi minus is a 139.6 MeV. The proton rest energy is 938.3. We're not using 10-digit decimal place here because we're just giving rough estimates for our energy. So I'm not going to do the 20 decimal places that we know the proton and the neutron are. The rest energy of the neutron is 939.6. The rest energy of the pi naught is 135 MeV, approximately. So once we know all of these, we can plug that stuff in here. The A is the pi meson, so there's the pi. I put the pi in there. The B is the proton, so I put the proton number in there. There's the divided by 2. Here's the plus. The C was represented by the neutron, and so I put the neutron value into there for C. The D right here is represented by the pi naught is the D, so that's 135 MeV right there. And then these two were the A and B, which were the pi minus and the proton. So this is the pi minus, and this is the proton right here. And if you calculate that, we'll get 940 MeV is the neutron's total energy. That's not what we're looking for. We're looking for the kinetic energy of the neutron. So if you want the kinetic energy of the neutron, of course, it's the total energy of the neutron minus the rest energy of the neutron. We know the total energy of the neutron. That's what we calculated here is 940. So I plugged that into there. Minus, and the rest energy of the neutron I told you is 939.6. So we'll get a kinetic energy of the neutron to be 0.4 MeV. Okay, so we answered one of the questions. We also wanted to know the kinetic energy of the π0. And if you want to know the kinetic energy of the d particle, which is the π0, the formula is a little bit different than this one, but the only difference is this plus has changed to a minus. Otherwise, it's the exact same formula. So if you want to type that up in a calculator, just hit second enter, bring this back up, and just change this to a minus. Okay? Otherwise, everything is the same. So this will still be 139. This will be 938 divided by 2. This will be 939. This will be 135. This will be 939.6. 135 will go in here. It'll look exactly the same as this, except this will just change to a minus. So there'll be a 139.6 here and a 938.3 down here, okay? So once you type this all up again, just put a minus in there, and you type it up, you'll get 137.9 MeV for the total energy of the d particle, and the d particle, of course, was the π0. So the total energy of the π0 is 137.9 MeV, and we wanted to know the kinetic energy of the π0, and so we'll get the total energy minus the rest energy. Do you know the total energy of the π0? Yeah, 137.9. Do you know the rest energy of the π0? Yeah, I told you that right here. It's 135. So this minus this, of course, is 2.9 MeV. So we've studied now these type of reactions. These formulas, again, are very dependent on the structure of this formula, these reactions. So make sure these two particles have velocities very much smaller than the speed of light, and then these formulas will work if you have reactions that look like this. I hope you enjoyed this lecture. I look forward to any comments at the bottom. Thank you very much.